Good morning. So welcome to the mathematical part of Newton's laws of motion. So to recall, we have law of inertia, which says that an object at rest tends to remain at rest unless acted by an outside force. So there are forces acting on the box, on the yellow box on top of the table is this is the pair forces, the force of gravity, the force of the table on the box, and the force of the box on the table going downwards. So let us, these are again pair forces. So if we include Earth, the Earth is also pulling the box downward, and at the same time as the reaction force of the box is pulling the Earth towards itself. And we are left with the force acting on the box, because if we are dealing with law of inertia, we are always referring to the forces acting on a certain object, or in this case the forces acting on the box. So the forces acting on the box, we have here the normal force, the force going upward, or the force of the table on the box, and the force of gravity on the box is they are both equal in terms of magnitude, so they cancel out. So our net force for our the forces acting on the box is zero, meaning to say all the forces, the normal force and the force of gravity, cancels out because of they are acting in the opposite direction and they are also equal. So in terms of equation, we have the summation of the forces in the y is 0. So we are asked, if the mass of the box is 10 kilogram, how much force does the earth exert on the box, or how much force of gravity does the box feel, and how much does the table exerts on the box, or how much force does the table exerts on the box, or how much is the normal force. So to answer this one, we have first to state that the summation of the forces is 0, wherein net force is 0. So there in this example, we have here the force, normal force, and the force of gravity is both on the y-axis. So we will have it here, the summation of the forces in the y, or all the forces in the y, is equal to 0, or they sum up to 0. And the summation of forces in the y includes the normal force and the force of gravity. Now, given the mass of the box, which is 10 kilogram, to compute for the mass, the force of gravity, that is equal to the mass of the box times the gravity or acceleration due to gravity. Our mass of the box is 10 kilogram, and then our acceleration due to gravity is 9.8 meters per second squared. So the force of the gravity now is equal to 98 Newton. So the unit for mass is kilogram, and then the unit for acceleration is meters per second squared. So if you combine kilogram meters per second squared, that is just the same as Newton. So if we already know the force of gravity, that is, we will have to substitute it here. So we have the summation of the forces is equal to, or the summation of the forces in the y is equal to normal force and the force of gravity. So we will, since force of gravity is directed downwards, it has a negative symbol. So this now becomes normal force is equal to force of gravity. Then substituting values for force of gravity, which is 98 Newton. So we are left with a summation of the forces is equal to 0, that is equal to normal force minus 98 Newton. And then transferring 98 Newton to the other side, so that we are left with normal force. So the result is normal force is equal to 98 Newton. So clearly you can see that normal force is equal to the force of gravity. Next, if we have this situation, a rock that is suspended in the air, tied to two ropes. We have here the rope. The first rope is tied on the ceiling, not at 60 degrees from the horizontal, and the other rope is tied to the right wall. So that is horizontally towards the vertical wall. So drawing the free body diagram, we have this result already in our previous discussion. So we have force of gravity downward, then tension 1. The tension 1, or the tension of the spring as it pulls the rock uh, to this direction, and tension 2 is the force of the string as the string pull the rock to this direction. So if this one here is 60 degrees, then this one is an opposite angle of this angle right here, so this one should also be 60 degrees. So we have here an angle, so this line right here is just parallel to the mirror line or mirror image of your force of gravity. So this one is parallel, so this one is just the same as the value of Fg, or the T1y, since this one is in the y-axis. So our T1y is equal to the value of force of gravity. And then our T1x is the x component of our T1, which is also equal to the T2 here. Again, T1x here is equal to T2 here. And then T1y here is just equal to the value of Fg. So how do we compute now? So if the mass of the rock is 10 kilogram, how much force, or how much force of gravity do we have here? And how much does the string T1 and T2 exerts on the rock? So we are going to compute Fg, T1, and T2. So the summation of the forces is 0. Summation of the forces in the x is 0. And the summation of forces in the y is 0. Now why is this all zeros? Because again, the law of inertia states that an object at rest should remain at rest. So this rock should remain at rest such that its net force along the x and its net force along the y should be 0. So our summation of the forces in the x includes T1x and T2. So again, this one is our x component, or the horizontal axis, and that force includes an actual force T2 and a component force of T1, which is T1x. And since this one is on the negative side of our axis, of our x-axis, so we have it here negative. So since this one is just 0, so we will remove that one, transfer this one to the other side. So we have an equation. So how do we compute for T1x? So we have here the formula for T1x. We use trigonometric function. So that is, we use this opposite side because we know this one to be equal to Fg. And we use this one so that we could compute this value, or the value of this side right here, T1x, which is just equal to T2. So computing or solving for T1x, which is just equal to T2, is just the same as solving for T2. So we have here, we need the opposite and the adjacent. So that is from SOHCAHTOA, that is TOA, that is opposite over adjacent. So that's why we have tangent 60 degrees is equal to opposite, or T1y, over T1x. So write it here. So we have here our T2 is equal to T1x, wherein our T1x is equal to T1y over tangent 60. So we rearrange this one. So we just switch this one to that place right there, and then our tangent 60 replacing T1x. So that is how you manipulate the equation. So substituting values now, we have our T1y, which is equal to Fg. So how did we compute Fg? That is mass times acceleration due to gravity. Since the mass is 10, so 10 times 9.8 is equal to 98 Newton. And then tangent 60 degrees is equal to 1.73205. So 98 divide the denominator, we have 56.58, or approximately 57 Newton. Then we now have solved T2. So next, we are going to solve for, now the FG is not anymore shown because we already, the FG is here. So although FG was used in the Y component or in solving for T1, we already have computed it here, which is equivalent to 98 Newton. So the summation of the forces in the Y includes the Fg, the force of gravity, and this one right here, the mirror image of Fg, which happens to be the T1Y or the Y component of our T1. So T1Y plus the negative value of Fj, because this one is directed downward. So rearranging the equation, we have T1Y is equal to Fj. So solving for T1Y now allows us to solve for T1. So this is how force of gravity is computed, although we already have it here, the value here. And then our value for, so how did we get T1 out of T1Y? That is using this formula right here. So the T1Y is in the opposite side of the angle, and T1 is the hypotenuse. So that is opposite over hypotenuse. So we can use sine from our SOHCAHTOA. So sine, the opposite is T1Y over T1. So rearranging this equation will gives us T1Y is equal to sine 60 degrees times T1. So this value for T1 is equal to sine 60 times T1, which is equal to Fg. And then substituting, rearranging now, we divide it with sine 60, so that's why we have sine 60 here on the denominator. So divide both sides with sine 60, so we are left with T1. So T1 now is equal to force of gravity divided by sine 60, wherein the force of gravity is 98 divided by 0.8660. So the value now for T1 is 113 Newton. So clearly, we could see and confirm from our free body diagram that T1 should be longer than force of gravity. And this one, T2, has the least value of force. Meaning to say, among the three, string 1 is exerting more force than force of gravity and T1. So we can confirm it from our computation that T1 has the greatest or the highest value in terms of the force exerted. Next, we have this situation. So we have here a rock that is not sliding on an inclined plane. The inclined plane is at 40-degree angle, and we are going to solve for Fg, Fn, and friction force. So this is our free body diagram, and this is our illustrations of the situation. So this one is 40 degrees here because the inclined plane is inclined at 40 degrees. So if we draw a line parallel to this one, just like this one, so this one also will be 40 degrees. And if this angle here is 40 degrees and this one here is parallel, perpendicular, so this one should be 90 degrees. So 90 minus 40, so this angle right here should be 50 degrees. So this should be enough now for our computation for Fn and F. So if you look at here, this one is the mirror of our force of gravity. This green line here is the mirror of our force of gravity. And we were able to create a right triangle between or among friction force, uh, force of gravity mirror image, or just the same as the force of gravity, and the mirror or the parallel, a line parallel to the normal force, which is just equal in terms of magnitude to the normal force. So we can just say that this one could be equal, or this one is equal to the normal force, and this one is our friction force, and this one is our force of gravity. You follow? So we can now solve these values right here. So let's start. So first, solve for the force of gravity, which is just mass times acceleration due to gravity. So in this case, it's not given, it's given here 10 kilograms. So that is 10 times 9.8. We have force of gravity is equal to 98 Newton. To solve for F, or the friction, we have here, angle here is 50. Angle here is 50. So F is adjacent to the angle. So we can use adjacent over hypotenuse, because hypotenuse here is given, which is equal to Fg. So we now have cosine 50 is equal to friction divided by force of gravity. Then rearranging that one, we will have friction force is equal to cosine 50 times force of gravity. So substituting values, we have cosine 50 is equal to this value right here, and then force of gravity is equal to 98 Newton, and our friction force is equal to 63 Newton. Still less than force of gravity. So this confirms that force of gravity should be greater than the friction force. And to solve for our Fn, we have here our Fn, and Fn is on the opposite side of the angle. So that is opposite over hypotenuse. So we have here sine 50 is equal to Fn divided by Fg. So rearranging the equation, we have Fn is equal to sine 50 times Fg. And this one here is the value of your sine 50 and the value of Fg, which is 98. So the normal force is around 75 Newton. Again, it's still less than the value of Fg. Or if you look at the drawing, Fg is longer than Fn. Now, you might be wondering, we are given with 40-degree angle and we used here 50-degree angle. Now, we can use the 40-degree angle. We just use 50 because it is in favor with our drawing, based on our analysis, that if this one is 40 degrees here, this one is 50 degrees. So we were able to create a right triangle in this angle right here using 50 degrees. But we can also use the other side of our rectangle here, which is part of our two right triangles. So we can use this part right here. We can use this one here and this one here, and this one will be our triangle. So we'll just erase. So again, our right triangle here, we can use this and this one and this one to be our right triangle. So this is just the same as in terms of value. This is just the same. So if this one right here is 50, so this one will be 40 degrees. 40 degrees. So we now have this one will be our F, this one will be our FG, this line right here, and this one is our Fn. So to solve for F that is opposite to the angle, so that is sine. So that this should be solving for F will be sine 40 degrees is equal to F over Fg. So see the difference? We used sine 40, which is just the same as cosine 50. Do you follow? And then for this one here, so our Fn is adjacent to the angle, so that will be cosine 40 degrees is equal to Fn, or adjacent, over hypotenuse, which is Fg. So this is now in favor with our given. So we just happen to use cosine 50 because it is how we got our first right triangle from the drawing. So because we started here, then we have 50, then and we were able to form a right triangle, then right away we solve it. But then again, if you solve it using this equation, that will just be the same. The same result you will get. For F, it will be 63 Newton, and for Fn, it will be 75 Newton. Okay, next. Now this time, law of acceleration. This time the rock now is accelerating. So looking at the free body diagram, we have here Fg is longer than the 2, it's longer than Fn, longer than the net force. That means that the value of Fg should be greater than Fn and Fnet. And still, the mass of the object is 10 kilogram, and the angle is 40 degrees. So this angle right here is 40 degrees. Then this angle also here is 40 degrees. Then, if this one is 40 degrees and this is perpendicular, if the mirror line and the horizontal surface, or the horizontal line, is perpendicular, that means it's 90 degrees. So this one will be 50 degrees. And then opposite to 50 degrees is this angle right here. And if this one is 50 degrees here, this one is also 40 degrees. So from this, we are able to create a right triangle, which is this triangle right here. Again, this triangle right here, we are able to create a right triangle. You follow? And then, so to start, solve for force of gravity first. So that is mass times acceleration due to gravity, which is 10 times 9.8, which is equivalent to 98 Newton, our force of gravity. Next, solve for Fnet. So Fnet is here. We used again the angle 50. So that is adjacent. This Fnet is adjacent to 50 degrees. So we used cosine, because we will be needing Fg. So that is cosine 50 degrees equals Fnet. So opposite Fnet divided by hypotenuse, which is Fg. So rearranging the equation, we have Fnet is equal to cosine 50 times Fg. And that is, or this value right here is the cosine 50, and this one right here is the force of gravity, which is 98 Newton. So the answer is 63 Newton. So almost the same as the one we had in our previous example. Next, we solve for normal force, which is this one right here, which is just equivalent to this line right here and this line right here. So that is now, this line right here is opposite to the angle, so we use sine. So opposite over hypotenuse. So opposite is Fn, hypotenuse is Fg. So rearranging the equation, we have sine 50 times Fg. And then the value for our sine 50 is that one, and 98 for our force of gravity. So we have 75 Newton as our normal force. So again, if you use the other side of the drawing, if you want really 40, you can use this right triangle here, and you can use that 40. So this one is the Fnet, and this one right here is the Fn. So using this angle, Fnet is opposite to the angle, so that is sine 40 degrees is equal to Fnet over Fg. And then for our Fn, which is adjacent to 40 degrees, so that is cosine 40 degrees is equal to Fn over Fg. So the answer would just be the same. Okay, next we have Newton's third law of motion. this I was not able to create a quiz for this one, so maybe in the next quiz this will now be included. So according to Isaac Newton, that for every action there is equal and opposite reaction force. So force action is equal to force or reaction force, and that is negative. So this value right here is negative. Not anymore negative, because this is already in between equal sign. So we'll just remove the negative here. So they are equal, meaning since they are of different, they're on the different sides of the equation. So their signs are negative if you wish to transfer. So we have here a 3-meter long cannon weighing 9,100 kilogram fires a 5.5 kilogram cannonball and accelerates it to 2,400 meters per second squared. So what is the acceleration of the cannonball if the cannonball is not braced to the ground? So usually a cannonball is braced to the ground to prevent it from moving to the opposite direction as the cannonball is fired, because that is always the reaction force. So for every firing, there is in guns we call it recoil. In the cannon, it is still recoil, and then the result is it will be moved backward. So with the weight or with the mass of the cannon, so I don't think it is a good idea to not brace the cannon. So again, force of cannon is our action force, and force of the cannonball. Yes. Our force of cannon is the action force, and force of the cannonball is the reaction force, or either. So for as long as both of them are in the opposite direction. So in terms of formula of force, we have mass times acceleration. So this is not about gravity here, because the movement here is horizontal. So we'll just use A and not G. So force of cannon is MA is equal to force of cannonball, which is also MA. And then substituting values now, the mass of the cannon is 9,100 kilogram times acceleration, which is equal to the mass of the cannonball, which is 5.5 kilogram, times the acceleration of the cannonball, which is 2,400 meters per second squared. So rearranging the equation or solving for acceleration, we have this one. And then the value for acceleration is 1.45 meters per second squared. So you would expect that if the cannonball is not braced, then this that the cannon is not braced, then you would expect that the cannon would be moving or accelerating to the left at 1.45 meters per second, especially if the surface is frictionless. Then you would really see that this one is accelerating to the left at 1.45 meters per second squared. So that will be all for our discussion. That will be all for the computation and the mathematical part of Newton's laws of motion.